Good morning. My name is Scott Marco. I'm the event coordinator here at the Society of Plastics Engineers. I will be introducing today's speakers for today's webinar entitled Robust Plastic Product Design, a Holistic Approach. This webinar is hosted by the Society of Plastics Engineers and sponsored by Geometric. Our two speakers today are Vikram Bhargava and Nikhil Dalvi. Vikram is a fellow of the Society of Plastics Engineers and a past chairman of its Product Design and Development Division. He recently retired as the Director of Mechanical Engineering Services at Motorola Solutions in Holtsville, New York. He has over 40 years of experience in product design, development, manufacturing, and management, especially in plastics. He is a sought-after trainer and has trained thousands of engineers and suppliers in the proper design and manufacturing of plastic parts and assemblies in the U.S., China, Taiwan, Canada, and India. He is a certified Six Sigma Bank Black Belt and has led or mentored numerous projects, resulting in millions of dollars in savings. He is currently authoring a book on holistic product design to be published by Hanser in 2016. He holds or has pending over 21 U.S. and international patents. Nikhil Dalvi is a senior subject matter expert at Geometric with a diverse experience in manufacturing, development, project management. Nikhil now provides consultative solutions for customers in the U.S. around this Geometric suite of technologies and products and addressing the design and manufacturing space. I'll now turn it over to Vikram.
Thank you, Scott. Here's some quick instructions if you want to talk about it.
Sure. So in order to ask a question, there's on the side you'll see there, and he has a nice picture of it. You can raise your hand, and we can call on you when the time has come. You can also enter your questions in the question box, and we will be keeping an eye on that. And the other button is to go full screen so that you get a better view of the PowerPoint as he's going through it. During the Q&A session, we ask that you submit your questions via the chat window, and the recording version of the webinar will be available on the DFM Pro website. So we will be doing a Q&A session at the end, and I think that's it. So Vikram, go ahead.
Nikhil, before I start, do you want to give a quick overview of Geometric?
Yeah, absolutely. Thanks, Vikram. So Geometric is a global company with a revenue of $180 million, and it is headquartered in Mumbai, India, but it has offices across the globe, with the U.S. headquarters being in Troy, Michigan, and that's the location where I am also based out of. So Geometric works in different areas in the product realization space with a specific focus on the design, manufacturing, or I'll say product engineering. And we also do a lot of PLM consulting solutions and various other software development solutions as well. So our customer base is majority of the automotive, aerospace, and commercial vehicle OEMs and the major tier ones. And we have a unique solutions that is something which is the differentiator of Geometric. As really we have got a suite of products and technologies in the design, manufacturing, and visualization space. And today we'll be touching upon one of them, which is DFM Pro. Yeah, Vikram, we can proceed.
Thank you, Nikhil. Good evening, good morning, good afternoon, depending on where you are. Let's start with the basics. What is a robust design? If this was a live session, I would have asked you the question, but we are, I'm just staring at a screen right now. So let me answer the question myself. It should perform as intended over the projected life and intended environmental conditions. This is very, very important in the case of plastics. Meet the appearance requirements, also very special requirements for plastic parts. And naturally be as cost effective as possible. Let's look at the total cost of a part. Let's say we are going to make n number of products during its life. The legitimate costs are the normal development costs plus tool cost plus cost of plastic processing material and profit per part that the supplier charges multiplied by n. The avoidable costs are additional resources spent to fix errors plus additional tooling costs plus scrap cost. And beyond avoidable costs are the warranty costs, liability costs, and opportunity costs. Let's look at the avoidable and unavoidable costs in general. We are all familiar with this curve. At the concept stage, it doesn't take much to change a design. As you move on to the right, in production design review, it takes a little bit more, but you can still make changes without too much turbulence and too much cost. But once you go into tooling and once you go into pre-production, into production, and beyond production, it can be huge. The cost can be huge. So let's try to keep all our changes in the left half of this curve. If we make our changes in the right half of the curve, it can cost a lot more money than it should, and perhaps cost millions of dollars. Let's think about the General Motor issue with the ignition switch. So let's not get into that situation. And also, the time needed to fix issues in general is proportional to the cost of fixing issues. So again, fixing issues in this stage is much quicker. It may be a matter of minutes, days, or weeks. Here, it could be a matter of months to fix, years to fix, as in the case of General Motors. Let's look at the typical curve from cradle to grave for a product. We introduce a product, it grows, it becomes mature, and then it meets its old age, it declines, and finally it comes to the end of sale. So this is the dark curve is the intended curve for a product that's going to be released. What happens if it's 4 weeks late? Really, you lose a lot of, you just don't lose from here to here. The whole curve is lowered. And the loss you have could be in with a 4-week delay due to some issue with a plastic part can be in millions of dollars. And what about the competitors getting a head start in introducing the product? They may have a similar product which was just behind you, and now they're ahead of you, and they're basically they have killed your product because they introduced it first. And additionally, what about the effect on future sales due to the bad reputation earned? Again, what we are hearing about Volkswagen and the issue with their emission control. These things, customers remember this for a long time, and they're not inclined to buy your product if they see problems with it. So let's look at the plastic parts as compared to metal parts. Why are plastic parts different from conventional metal parts? Published properties in the case of plastics are only guidelines. I'm going to show you a typical spec sheet. We're waiting for it to come out on the stage. Yep. So this is a typical the spec sheet for a plastic, for a polycarbonate from SABIC. And although I'm using SABIC example, every resin manufacturer has similar conditions for use. It says only typical data for selection purposes, not to be used for part or tool design. Each user is responsible for making its own determination as to the suitability of the product, seller's product, through appropriate and use and testing. So in other words, these properties are only a guideline compared to metals. If you look at the 80,000 psi tensile strength of a cold rolled steel, by golly, it's going to be 80,000 regardless of where you buy it from. You can take it to the bank. Properties are affected by the environment, temperature, time, and relatively unpredictable. And I will go into more details of this. Properties in metals are not affected by normal environment, temperature, and time. Even if they are more readily predictable. I live next to New York City, and I use the George Washington Bridge every day, or every week. It's 85 years old. Nothing basically has happened to it in the 85 years. Yes, it's rusted a little bit, and it's been painted a few times, and they've changed a few of the components. But it has not been in 85 years of that real harsh environment. Nothing substantially has changed to the properties of the metal. Plastics have unique design requirements, which are generally not taught in engineering schools. Metals have conventional design requirements that we all are very good at in our education. Engineering education does a good job of letting us be familiar with these rules. Tooling and processing can have dramatic effect on performance, as I'll show in the slides to follow. Tooling and processing have relatively little effect on the performance. The metal part of stamping, a die casting, a casting, a forging, depending on tooling and processing, you'll have a good part or a bad part. It's not going to be processing, not going to have a dramatic effect on the ultimate properties of the part. It's going to be good or bad. If the die casting tool is bad, you're going to have a bad angle or burr on the part, but you'll know it and you'll fix it. Plastics have a lot of latent defects that cannot be detected with routine quality control, and that will come back to bite us. There's very few latent defects in metal parts that cannot be detected with routine quality control tools. Let's look at a few examples. I'm waiting for the slide to update. Okay. Now, die casting is a very common metal process for creating finished parts. And one of the biggest issues with die casting is porosity. You can see porosity right on the surface, in this case on the right, or if you can't see it on the surface, you can see it with conventional X-ray equipment, as you can see on the left. So there's really almost no latent defect that will go undetected with proper quality control techniques. So given all the complexities of plastics, I am recommending a holistic approach for plastics product design. Basic definition of holistic: relating to holism, emphasizing the importance of the whole and interdependence of its parts. Concerned with wholes rather than analysis or separation into parts. So, one of the most common things is holistic medicine. Holistic medicine is not just taking a pill when you fall ill. Holistic medicine is controlling your diet, controlling your mental state, controlling your breathing, controlling your physical activities, controlling your food, and if needed, getting some medication. That is the holistic approach. So what happens if we apply to the holistic approach to a plastic part? Let's assume that the plastic part or product is a high performance car. The 4 components, and it has 4 wheels, that it has to have in good condition for it to perform. And these wheels are tooling, material, processing, and design. All of the 4 wheels have to be properly inflated and be of the right quality. You have one bad wheel, and you can have a situation like this. And this is a serious matter. So this wheel can be processing, it can be tooling, it can be design, or it can be material. Any of these can cause a disaster to happen. On the other hand, if you take care of these 4 wheels, you could have a product like this. Now this video is slow to catch up with you. What I'm showing you is one of our products that I was involved with being thrown around in a warehouse, being thrown to a height of 30 to 40 feet, bouncing back onto the concrete floor, banging it around, using it like a hammer. Now here he's using it like a hammer, kicking it around. He's banging it on the floor, he's kicking it around. He's again throwing it up in the air. and it still performs. Now he's going to use the product to scan a scan a barcode, and it does it well. This product had a glass front, it had plastic parts, it had delicate internal members, and it was thrown around, it was used as a hammer on a concrete floor, and nothing happened to it. Not the performance, not the appearance, no broken parts. Let's go back to what David Wright wrote in his book, Failure of Plastics and Rubber Parts. He looked at 1,000, I think he looked at 1,000 failures and classified them into this pie, where it said 20% was due to design, 20% was to processing and tooling, 45% of the failures were due to poor material selection or poor material performance, and 15% due to customer abuse. I would like you to keep this chart in mind as we talk through the slides. So now David Wright says 20% of the failures are due to design. Let's look at the biggest piece of the pie, materials. Now in the metals world, if we were coming from the metals world, normally we would, and if we were looking at the properties of the plastics, from the metals world, we would look at the green ones, which is mechanical, tensile strength, toughness, maybe elongation. We might look at resistance. We might look at chemical resistance. But all the properties in the black are properties that you have to look at very carefully if you're designing a plastic part. We have to also deal with issues in terms of materials with UL approval, FDA, ROS, which is an international requirement right now, a restriction of hazardous substances. There are 6 substances. We don't have time to go into details. Everybody has to be aware of ROS, country-specific requirements. We need to look at molding properties. As mechanical engineers, do we think about flow? Do we think about bonding between materials? If you have an overmolded part, soft plastic over hard plastic, or directional shrinkage, plastic shrinking by a certain amount in one direction and a different amount in a different direction, causing all kinds of problems. Going back to design, looking at the same thing from the metals world, we look at the tensile strength, toughness, elongation, etc. But in the plastics world, we have to look at the electrical properties, electrostatic discharge, ESD properties. We have to look at the molding and tooling dependent requirements. We have to look at the gauge size, appearance and location, midline locations, appearance, wall thickness uniformity, wall thickness ratio, thick to thin flow, sharp internal corners, midline, orientation, draft, boss length. All of these will affect the ultimate performance of our plastic parts. And we, as the mechanical engineers, designers, have to look at that. Let's go to processing. Now, when we design a metal part, we basically let the processor do what he or she needs to do, and we generally get a satisfactory product. But all of these can affect the ultimate performance of our plastic part. Material drying, residence time. You may not be familiar with all these terms. I think you should become familiar with these terms because these are very important. Material heating, shear rate, injection time, packing time and pressure, gate freeze, mold heating and cooling. Extremely important. Poor mold heating and cooling can really, really make your part perform like, totally in a improper way, in an unsatisfactory way. Venting, cooling. All of these are extremely important that you as a designer need to be aware of. Again, going to tooling, runner and gate design, flow balancing, cooling, ejection, multi-cavity balancing, vents. These are not just the toolmaker's problem. They are also your problem. They are your issues as the designer. And ultimately, you're being responsible for the performance of the part. Very few parts just get molded and shipped and put into use. They have secondary operations like ultrasonic assembly, heat staking, insert molding. You put screws into it. You put silk screening. You decorate it with silk screening. You do pad printing. You do hot stamping. You paint these parts. You, as a designer, need to be responsible to make sure all these operations can be done satisfactorily and that your material will be capable of being painted. You can't take a nylon part and hope the paint will stick to it. If you're making a nylon part, you have a real problem painting the part. So you have to be aware of these things. Basically, it comes down to this. Basically, it comes down to this. Plastics do not take long-term stress as well. These stresses can be the result of a continuous load, warpage, or many other design, material processing, or tooling related issues. Therefore, any design, tooling, or processing issues that induce avoidable long-term stresses should be avoided. Let's look at the plastic fundamentals for a second. When the part comes out of the mold, you have a relatively cold mold wall on both sides of the plastic. You have material coming in at 500, 600 degrees F or 300, 400 degrees C. And plastic is basically a very, very good insulator. So the material in contact with the metal wall gets cooled very fast. The material in between stays hot for a long time. Now the material starts to shrink. The inside layers are hard. They continue to shrink for a much longer time than the outside layers, which have already cooled down. What does this do? The inside layers try to pull the outside layers in. The outside layers try to pull the inside layers out. What happens? You have layers of compressive stress on the outside and tensile strength in the middle. Now, compressive stress on a mechanical part is your friend, because most of these stresses are tensile, and compressive stresses also increases the resistance to chemicals on the plastic. So you want to have this nice compressive stress layer on both sides of your plastic. What happens when you bend the part? Here's the simulation of a dog bone, which you see the shadow here being bent. And I'll show you a simulation that Joe McFadden, the person I used to work with at Motorola, did. It'll take a second for it to show up. Okay, so you have this. When it's not bent, you have this blue compressive layer on the top. Now, what happens when you bend it? You can see the compressive layer is turning into a tensile layer, and you're introducing a tensile stress on it. Okay, so we take the same dog bone and we bend it back and forth. We are taking this same tensile bar and we are bending it back and forth. You can't see it very clear in the video, and nothing happens to it. You can do it for hundreds of thousands of times in the case of polycarbonate, and nothing will happen to it. You take the same tensile bar and you put a drop of solvent on it, as my wife is doing here, and you have a catastrophic failure. You can see the bar completely broke in the middle and left this really rugged edge. So a plastic part which was fine, unbent, and with the slightest amount of bending, now it's very, very sensitive to solvent. And it doesn't have to be harsh solvents like acetone. Even something that you put on your hair, the Trust Me hair gel, if you have a headphone made out of polycarbonate and you're unbending in the process of putting it on your ears, even the Trust Me gel will act on it and crack the headphone bar that's connecting the two sides of the headphone. let's go back to David Wright. He said within the 45% failures of the material, which is 45% of the pie, 25% of the product's failures are caused by environmental stress cracking, ESC, and with an additional 7% from chemical attack. That makes it 32%. 32% of 45% is 15%. So roughly 15% of the plastic parts fail due to chemical attack or environmental stress cracking. And so a lot of it is in our hands to make these plastic parts robust against ESC and chemical attack. Here's a handheld device that has cracked right here just from the use of lotions on the operator's hand. And I'll talk about it a little bit in the end. But keep this in mind. Just from the use of lotion. Now, we're not talking about harsh solvents. We're talking about hand lotions that you normally use, creams and Vaseline that you use in hand. That's caused this part to crack in a very dramatic fashion. There's a lot of rules to follow in the case of plastic parts to reduce the stresses. And if you do any Google site, you'll come up with all these items. If we talk about DFM Pro in a few slides, DFM Pro has a list of all the rules that you need to follow. But I'll talk about a few key rules that that if you violate, we get into serious trouble. Wall thickness to vary no more than 25% for amorphous materials like polycarbonate, PC, ABS, and acrylic, and 15% for semi-crystalline materials such as nylon, polyethylene, and polypropylene. In other words, if your nominal wall is 100,000 in the case of polycarbonate, you shouldn't have any section less than 75,000. And if you have the same in nylon, you shouldn't have anything that's less than 85,000 in the case of nylon parts. The rib thickness at the base has to be no more than 50% to 60% of wall thickness. We don't have time to go into the details of this, but just take it here and go back and do some reading on it. So what happens if you have a non-uniform wall? This is a part that has been by design made into a very rapid transition in thickness from the left to the right. The right is 200% of the left in terms of thickness, and this is how it comes out from the mold. This is infrared photography of the temperature of the molded part. You can see on the left side, the part has a lot less heat content and is cooled down very rapidly. And when it comes out of the mold, it's at 118 degrees C. And the left side has a lot more heat content, which is still cooling down, and it's 238 degrees. What happens at the junction? The left part is trying to contract for a long, long time. The right side is contracting for a long time, and the left is already done contracting. So what happens at this junction? A very, very, very high stress layer. You put a solvent in this section, it'll basically crumble before your eyes. We've introduced a very high stress, and therefore made it very, very, they've taken out the resistance to chemicals in a dramatic fashion. Here's a part from from a car. I'm not going to tell you the brand and country of origin, but this is a car that's very commonly in use across the world. Here's the turn signal lever and washer wiper signal. Now the problem with this part is, if you can see this section here, this is connected to this section with this very thin area, which is about 100,000 in thickness, and this thickness goes up to about 300,000. Now you have a section thickness varying from 100,000 to 300,000, resulting in a very high stress in here. And the normal use of basically lifting the lever and lowering it to operate the washer, the wipers, made it to fail. Luckily, the operator, I knew the operator, the driver of this car. Luckily, she escaped serious injury, but this could have been disastrous. And you know, shame on automotive suppliers for letting parts like this go out into critical parts of the automobile. But this happens more often than you and I imagine. Don't let your part be a victim of this. Inside radius. This curve applies to not just plastic parts, it applies to, again, this curve, the studio slide just refreshed. So again, I'm repeating myself. This curve applies to all metal parts, not just plastic parts. If you have a very sharp inside corner, you have very high stress concentration, which basically means if the part is under stress, it's going to break at the area which has a very high stress concentration. It's going to raise, it's like two baseball players trying to catch a fly ball. One of them raises a hand and says, I'll get it. Well, this sharp corner raises his hand and it says, I'll fail. Don't worry about the rest of the part. Don't fail. Don't worry about it. I'm going to fail. And it does. So basically it shows that if this is the thickness of the wall, this is the radius, and this is the radius thickness ratio. If you have a thickness R by T ratio less than 0.5%, you're going to dramatically raise the stress concentration. If you go to the right, you're going to reduce the stress concentration, and the part will fail not at that corner. It will fail anywhere in a random fashion, which is what you want. Plastics have their limitation where you cannot go to 1.0 and 1.2 because other constraints plastic parts have, which we don't have time to go into. But let's say the minimum radius should be 0.5 and the ideal radius should be 0.75 T. If you don't have that radius and you have sharp corners, you can see here there's a sharp corner under this boss and the connecting ribs, and you can see even without any use, you can see these very high stress marks. And what happens in a drop? It completely shears off at this area. This is where it fails. If this corner raises 10, boss, I'm going to fail here. Don't worry about the rest of the part. Don't worry about it. I'm going to fail right here. I've got it. And it did. What is the issue here? This is my car. And what I'm showing you is this very, very straight crack here. I don't have time to go into details, but this is a knit line. If you have a hole in a part, if you have a hole surrounded by a plastic part, you are going to have a knit line. The idea is to have the knit line in the right position where it does. And knit line, by the way, is the weakest section of the part. It can have anywhere from high of 80% to almost 0% of the strength of the plastic in the as compared to the plastic in the adjoining area. So you cannot, if you have a hole in the part, you cannot avoid the knit line. But what you can do is have the knit line situated in an area where it is not prone to the high stresses, and also you can make it as strong as possible with your design, with your processing, with your tooling. Long unsupported bosses. So here's a part which has a long boss here. You can see this long boss here. We want this length to be no more than 3 times the diameter or 3 times the thickness, but here it's about 10 times. And this is a cross section of the boss. This is the outside of the boss. You can follow my arrow. And this is the hole inside the boss. Now you can see these are not concentric. They're supposed to be concentric. This hole is created by a slender pin that's going through this length, and that's subject to up to 20,000 psi of plastic pressure. It's acting like a cantilever with 20,000 psi acting on its tip, and it's going to bend, and it's going to bend, and ultimately it's going to bend back and forth, and ultimately it's going to crack due to fatigue. But in the process of bending, it's causing the hole in the boss to be not concentric with the outside. Okay, so that was a thin, slender piece of steel. Let's look at something really robust. Now here we have a piece of steel that is 10 inches deep, 5 inches wide, and 1.5 inches wide, 5 inches across and 1.5 inches wide. Very, very solid piece of steel, right? Shouldn't be affected by the plastic pressure, right? Wrong. The 20,000 psi acting on the tip of the steel is making it bend, and this wall on the left is not supposed to be half the thickness of the wall on the right. That has happened because the core, this massive steel core, has shifted. So this rule applies even if you have a big opening in the plastic part, and you need to have a proper consideration of the thickness or the diameter to height ratio. Here we have a part that has a thick area surrounding a thin area. So what happens is the plastic flows into the thick area, path of least resistance, and then it realizes, oops, I have to fill this area too. By this time the flow front the temperature has come down rapidly. It's not flowing. The pressure is reduced dramatically. So it doesn't have enough temperature, enough oomph in the pressure to fill this part. You're going to have a resultant void in the part. This is hesitation. And this is not just a visual defect. It is also a very high stress area. And if you apply any kind of chemical, not even a harsh chemical, this is where it's going to fail. So don't think of it just as a cosmetic failure. It has an inherent failure in the properties of the plastic part. It's not going to take the stresses as well. It's not going to take a chemical attack as well. And there's a whole area, a lot of area to cover, but let's talk about processing very, very briefly. There's a whole slew of things in processing that you have to be aware of, but one of the most common problems is poor drying. So going back to the basics, all polymers consist of random chains of molecules. And these are long chains, and the longer the chain, the tougher the plastic. Okay, so these are long random chains of molecules that make the plastic. Let's take the example of polycarbonate. Polycarbonate is the reaction of bisphenol A, the villain that we hear about, BPA. Not a villain in my opinion, but anyway, the villain BPA. This is the villain BPA, bisphenol A, and carbonic acid. And in the reaction, hydroxyl group and a hydrogen atom is expelled from these two molecules, and they combine to continue to become a longer and longer chain. And this reaction continues till the average molecular weight of the chain, in the case of polycarbonate, is about 50,000. Now, if you don't dry the material properly and there's moisture around when you're molding it under the high conditions of high temperature and pressure and humidity, the water enters the chain again, and basically you take the 50,000 chain and the hydrogen atom, the water molecule basically breaks it down into two chains of 25,000 each. And this continues to happen, and basically you take a pair of scissors and you cut up the chains if you don't dry the material. And it's going to dramatically reduce the strength and impact resistance of the plastic parts. Here's the case of poor drying. We saw the thermal being tossed around in a 40-foot ceiling, and here's a part that they made of PCABS that was not dried properly in processing, and crushed into and basically scattered into a million pieces with a 36-inch of drop, not onto concrete but onto carpet. This can happen to a good polycarbonate part if you don't dry it properly. So let's go back to this chart that we talked about, 20% due to design errors. Now let's look at I looked at 100 failures and I classified them into types of failure: flow marks, sharp internal corners, warpage, sink marks, venting defect, environmental stress cracking, scuff marks, tool issues, hesitation, and others. And I classify, and here's the table containing it. Now, so if you look at the flow marks, well, it's a processing issue, right? The processor didn't do a good job in either heating the mold or mixing the material or doing something wrong. That's very, very wrong. If you look at the causes, they're designated as 1, 2, 3, 4, and we move to this table on the left. 1 is rib thickness, 2 is wall thickness variation, 3 is sharp corners, 4 is long, thin ribs. All of these combine to cause these flow marks and visual defects. Not the processor, not the tooler. You, the designer, caused this problem. Let's look at warpage. Okay, the cooling of the mold was not right. The one side was cooler than the other. The cooling lines were blocked. Okay, I'll take that. That may cause it. But more than likely, it's caused by the fact that it is 1, 2, 3, 4, 5, and 7, which is rib thickness, wall thickness variation, sharp corners, long thin ribs, and steel height to base ratio. All of these can cause warpage. So don't assume that warpage is due to processing. Ultimately, most of these issues that we classify as tooling, material, processing, a lot of them can be traced back into design. And you as a designer is responsible for it. Let's look at in my opinion, this is, I'm pulling this number out of thin air, but I would say in my experience, I could say 70% of the issues are due to design. Mr. Wright says 20%. I would extend that piece of the pie to 70%. 70% of the errors are caused because of poor design. Not material, not tooling, not processing, poor design. Let's look at these again. Chemical attack, poor choice of material? No. There was a sharp corner here and it causes a very high stress concentration. That's why it failed. Avoids hesitation. It could have been controlled by better processing, better, higher melt temperature, higher melt speed, higher mold temperature. No. You cause the problem by surrounding a thin area by thick area. Warpage. Oh yeah, poor cooling the mold. No, the molder did as good as he could. You caused the problem with thin and thick sections right next to each other. This wall being uneven. Oh yeah, they used poor quality steel that didn't have the modulus that the steel should have had. Wrong. It was the steel was right with the right modulus. You caused the problem by making the core length way longer than the core width. So if you cause all of these problems, 70% of the problem, according to me, you may or may not agree with me. If you cause 70% of the problems as a designer, wouldn't it be nice to have a magic wand that could check the model just as a spell checker checks for spelling and grammar in Microsoft Word? Wouldn't it be nice? Nikhil, do you want to tell us about it?
Yep. I think that's exactly what we looked at, and when we started looking at this problem, we thought like I think we have sufficient technology and definitely something which we can definitely help our customers. So this is what we actually created, like a DFM Pro. This is a solution which we created with mostly the intention being creating this design for better performance, as Vikram was suggesting. And we have seen that for many, many years, organizations have been adopting some DFM and design review, gated process, but that process is still not completely implemented, and there are still some issues that still happen downstream, as we were seeing in many of the examples which Vikram shared. So what we really did, Geometric actually developed a unique solution.
Do you want me to go to the next screen?
No, I think we will continue with this.
Okay, let me know when I.
Yeah.
Yeah.
Yeah. So we created this kind of best practices repository, which Vikram talked about, the rib thickness, wall thickness, and all those kind of issues, right? So all those best practices are embedded into something what we call as the knowledge repository, and it runs and validates your designs against those. And while the design engineer is creating the design, these feedbacks can be given to the design engineer. And it is well integrated with the CAD system, so the design engineers can study and take a call immediately without really waiting for any formal reviews. So this way, the majority of the issues can be addressed before the design really goes out to manufacturing. And those iterations which happen between the manufacturing, the tool maker, and the design, those can be reduced. So I mean, can this software solve all the problems that Vikram talked about? Probably it won't, but it can definitely address majority of them. And there are a lot of criteria that we have already mentioned there, like where in the plastics design process itself, where we already have these kind of what we call as the rules, which can be addressed with the out-of-the-box solution called DFM in the DFM Pro. So we can go to the next slide. So the other thing that we have been discussing a lot about the plastic, but as this slide explains, like, we cannot just live with bread alone. We definitely need peanut and butter to make it tasty. So obviously that's where what happens in any product, like you just don't have all the plastic components in it, but it has different other parts like the sheet metal stand part, the castings and machine components, all of them are required. If you go to the next slide. So we actually have this solution which really addresses majority of the processes that are being used today, like machining, injection molding, and assembly. Additive manufacturing is like a new area where we are seeing that 3D printing is kind of taking off, and there will be lot many usages of that. That's where we are actually investing in that and creating some rule base for that. But casting and sheet metal stand parts, all these are the kind of processes which are supported with this DFM Pro solution. So Vikram, if you can go to the next slide. Yeah, so this is like, these are the kind of injection molding rules. If you go to the next one, these are the assembly rules where it looks at all the different interfaces between the components and if there is any issue there. Yeah, just move on to the next slide. Yeah, I think. So obviously we can share these details of what all specific best practices that are there, but I think we can get a lot of information on our website also. So right now, in the interest of time, we can go to the next one.
Okay.
Yeah, just move on to the next slide now. Yeah, so here, what we did is like, these are the best practices.
I'm sorry, 1 second.
Sure.
Oh. Okay.
Yeah. So these best practices or the rules, right? These are something which comes out of the box in the solution, but at every organization has their own way of defining certain things, and there are definitely certain tweaks which are needed, and that's why we have created this framework which is flexible enough to make these best practices or something which comes from the standards or design handbook into your own best practices. So there is a lot of flexibility to configure those and tweak the parameters to make it like your own rules book. Next slide. So what it really does for the organization is basically all these rules or whatever processes that we talked about, it can be used right at the design stage as a solution for the design engineer, and now you can actually do this in the automated way. So in a way, you are able to get this efficiency gain, and most of the savings related to the engineering time that can be definitely achieved there, and you can take the right decisions there. So the other part that you can definitely gain is the knowledge, and we continuously keep building this rule base as new materials come in, new processes come in. We keep on building that rule base, and in a way, your organization start gaining that knowledge from the external world through this tool. And the other thing that you can also get is like the new engineers who come out of the college, they do not have a good idea about the manufacturing processes. So with this tool, basically as you are doing the design, getting this feedback, literally you are learning as you are seeing these outputs from this tool. The other thing that, as Vikram also mentioned, like there is that curve that we saw about the impact on the cost when you have to make some change at the later stage, like when you are in the prototype or in the tool making, and that can create a lot of rework and scrap of the material of the tools, and those are pretty expensive tools. And those changes, if we can avoid or take the right decisions upfront, we can definitely help in avoiding certain issues and avoiding certain costs that get incurred today. It is also a solution which can help in data-driven collaboration. Like today, most of these design and manufacturing reviews are kind of person-dependent. But if we have this kind of output coming from the software, then there is a data which is getting generated, and now there could be a collaboration which is more focused with the actual data, with the actual results, and the right actions can be taken. And last but not the least, which is the quality. I mean, that is the whole idea about making this design to produce a product which can perform better throughout its life. And that was the initial thought that Vikram actually mentioned. What is the robust design? So finally, how can I make my product quality better? And that's the idea about having all these rules and reviews in place to get your designs better. Go to the next slide, Vikram, and I think you can take it.
Okay, so DFM Pro optimizes the overall inherent design to prevent short and long-term visual functional processing or tooling issues. We take it on to the next stage, flow simulation, mold flow, Moldex. That takes a sound design. It has to be basically a sound design, and then it optimizes it for a performance through proper flow, cooling, heating, venting, ejection gates, and location, strength of net length. In other words, the DFM has already taken care of the 70% of the issues that I talked about that emanate from design, and mold flow takes the next 30% and makes it almost 100% perfect. There's no such thing as 100% mold perfect, but 100% perfect, but it almost goes there. And together they provide a powerful 1-2 punch. DFM Pro uses flow simulation is dynamite. And concluding thought, this is a shot in a molder. I was with a tool maker, processing engineer. I was a design engineer, and I had a guy from Bayer. We worked together and created a really, really good product. And now we have a new friend that wasn't around when this picture was taken and called DFM Pro. And he or she is everybody's friend. So now there's 4 wheels plus DFM Pro. Okay, Scott?
Yes. All right. So now begins our question and answer session. And I did see a few questions come into the question window, so I will get to those. The first one was, would the presenters share their presentation with us after this webinar? My understanding is that a recorded version of this webinar will be available on the website. As for PDFs of any of the slides, I don't know how that's being dealt with, but a recording certainly will be available.
That will probably be more on a one-on-one basis. So we won't send it out to the world, but if a request is made, we'll consider it.
Okay, and this next this next question is asked by David Shatner. He asks, how can you tell after the fact that there has been inadequate drying and reduced molecular weight?
Okay, so you can do, it's a destructive test. You can do an MFI testing. And again, I say it's a destructive test. You just basically grind up the part, and there's a thing called mole flow index. You start with a mole flow of 20, let's say 10 grams per minute, and it should not go to more than, if it's processed properly, it should not go more than 20%. So 10 grams to 12 grams is acceptable, but if it goes 15 grams or 20 grams per minute, which means the plastic's flowing much easier now, which means the molecular chains have been broken up, then you have a problem. Unfortunately, it's after the fact, and so rather than do that, make sure the drying is controlled properly. And we can, if you want to send me an email, I can go into the details.
Okay, and it looks like we have time for one more question, which is also from David Shatner. And that question is, why is length-width ratio a root cause of core shift?
You're talking about the core shifting and causing non-uniform wall thickness in the boss. I think that's what you're asking. If I understood your question right, the hole is created by a piece of steel, and there's plastic all around it. This piece of steel is being subjected to up to 20,000 psi of plastic pressure, and it's like a cantilever, and it's got this load at the end of 20,000 psi, and it's making it shift. And the steel is not strong enough to resist this, and therefore it shifts, and therefore the plastic thickness changes.
Okay, so that will end today's webinar. Thank you to both Vikram and Nikhil for presenting today. Thank you everybody for attending. If there are any other questions that we didn't get to, we will do that over email. I just want to point everybody to this last slide here. That's the information, contact information for myself here at SPE, and questions that you have for our geometric. So if you have any questions or you need more information, feel free to reach out. And that will do it for today. Thank you all very much, and thank you again to Vikram and Nikhil.
Thank you.
Thank you, everyone.